Thank you for attending the first lecture of MET 212. Welcome to your first linear algebra lecture. Today we'll be looking at vectors in 2 and 3 dimensions. How do we define vectors? We define vectors as an ordered collection of numbers. What do I mean by ordered collection of numbers? Is that the numbers do not just form a set, they have to be in specific positions. So take an example of a vector v in 2 dimensions. It has components v1 and v2. This is a column vector and it has 2 rows, and each row has 1 component. So that is why it has only 1 column. So v1 and v2 are the x component and the y component of the vector. Now in 2 dimensions it makes sense to talk about x and y components. In 3 dimensions it makes sense to talk about x, y, and z components. But in higher dimensions we'd probably have to call them x1, x2, x3, x4, all the way to xn components. Now if we interchange v1 and v2, we don't have the same vector, we have a different vector. Now a vector is going to be denoted by a bold-faced v or w or any other variable here. Now if you're not using LaTeX or any other typesetting software, what you can do is you can underline your variable, or you can place an arrow above your variable, and so on and so forth. Now these components of our vector, they're going to be real numbers, and we can have vectors with complex numbers, and they're pretty easy to deal with as well. So I'm not going to go there. Now consider another vector w, 3, 3. How do we define vector addition? Vector addition is simple. You just add the corresponding components of the vectors. So v plus w is basically 1 plus 3 in the first column, in the first row, and 5 plus 3 in the second row. Now because the addition of real numbers is commutative and associative, vector addition is also commutative and associative. So v plus w is w plus v, and v plus the addition of w plus x is the same as the addition of v plus w plus x. Now, why do we choose to start with 2-dimensional and 3-dimensional vectors? We choose to start with these vectors because these are the only 2 types of vector that we can represent on a diagram. Now, consider the vector v given in equation 1. The starting point of a vector is called the tail of the vector, and the end point is called the tip of the vector. Now, what the important thing is that the tip of a vector, in our case v, has to be v1 units to the right, v as in v1 units along the x direction and v2 units along the y direction relative to the tail of the vector. For example, in figure 1, we start the vector v at the origin. Now we could have just as easily have started the vector v at 1, 1. It wouldn't really have mattered. But what is important is that the tip of the vector, as in where the vector ends, is 1 unit along the x direction and 5 units along the y direction relative to the starting point of v, or the tail of the vector. So because v starts in 0, 0, it must end at 1, 5. Now we want to add v and w diagrammatically. How will we do that? Now what we do is we use the triangle rule, and that is very simple. We place the tail of w on the tip of v, and we join the tip of v we join the tail of v to the tip of w to get another vector x. Now notice that the vector x has the components 4 and 8. And this is exactly what we expect, right? Because exactly what we expect from our addition, equation 3. Now you could have just as easily have done w plus v. You could have started w from the origin and placed the tail of v on the tip of w and gotten the same x. Why is that? Because vector addition is commutative. So v plus w is the same as w plus v. So x here is the magenta vector. Okay, now scalar multiplication. So if you have a vector v with components v1 and v2, and you want to multiply it by a real number, we call that real number a scalar. Right? So each component of v is multiplied by that real number. Let's call it c. So we end up with a vector cv1, cv2. Now cv is a vector that is parallel to v, but it is c times the size of v. So compare the blue and the green vectors in figure 2. Notice that the green vector is twice as long as the blue vector. The blue vector is v, the green vector is twice v. Because each component is multiplied by 2, the vector is twice the length of v. Now what happens if c is less than 0? You have a vector that points in the opposite direction. A scalar constant that is negative is going to reverse the direction of the vector. Now, because c is negative 1, you get a vector that has the same size. However, the red vector here is the same size, but it points in the opposite direction to v. Now, if you had another constant d, which is also a real number, and you form the expression cv plus dw, this expression is you would have formed the a linear combination of v and w, right? So cv plus dw, c and d can take on any real number values. There are linear combinations of v and w. Now, if v and w are parallel to each other, then you get vectors on the same line. You can try this out. Now, however, if v and w are not parallel to each other, you can choose c and d such that any vector in the xy plane or any vector in R2 can be represented as a linear combination of v and w. In this case, we say that v and w, they span R2. V and w, they span R2. You are probably familiar with this idea, with the idea of span. You may not be familiar with the term itself, but I know you're familiar with the idea if you've studied mathematics in high school. So, for example, you're familiar with the unit vectors along the x and y directions, I hat and j hat. So you can write down any vector in the xy plane in 2 dimensions as a linear combination of I hat and j hat. I hat and j hat, they span the xy plane. Alright. So of course, the same ideas apply in 3 dimensions as well. We could talk about vector addition in 3 dimensions. We can talk about vectors having a scalar multiplication, and we can talk about linear combinations in 3 dimensions as well. What about the inner product of 2 vectors? Now we define the inner product as a way of multiplying 2 vectors. We multiply the corresponding components. So for example, with 2 vectors v and w, we would multiply the x component of v with the x component of w, the y component of v with the y component of w, and the z component of v with the z component of w, and then we would add them, right? So we'd get v1 w1 plus v2 w2 plus v3 w3. So, and we can do this in an arbitrary number of dimensions. In 2 dimensions, we'd have v1 w1 plus v2 w2. In n dimensions, we'd have v1 w1 plus v2 w2, all the way to vn wn. Right. So, one example of the inner product is as follows, right? So, for example, if you've bought 4 different articles, each costing, okay, so 1 unit of an article that costs $3, 2 units of an article that costs $5 each, 3 units of an article that costs $7 each, and 4 units of an article that costs $9 each, right? So your total spending is then 1 times $3 plus 2 times $5 plus 3 times $7 plus 4 times $9. This is exactly the same as the inner product of the vector 1, 2, 3, 4 with the vector 3, 5, 7, 9. Okay, so this inner product is sometimes called the dot product. Now, so v, the inner product of v and w reads as v dot w. Now if if you have a vector w, right? So the inner product of w with itself is of course w1 times w1 plus w2 times w2 plus w3 times w3. So which is the square of the modulus of w, or the size of w, because you know this from Pythagoras' theorem. Now, if you have a vector w and you want the unit vector in the direction of w, you would divide w by its own magnitude. But since the magnitude of w is the square root of w dot w, you get w, so the unit vector in the w direction is w divided by the square root of w dot w. We call this w hat, right? We place a caret mark over w and we call it w hat. Okay, so now I'm going to make a claim. The claim is that the dot product of 2 vectors v and w is equal to modulus of v times the modulus of w times cosine theta, right? Remember, what is the definition of v dot w? V dot w is v1 w1 plus v2 w2 plus v3 w3. Now, I'm going to claim that this expression is equal to the modulus of v times the modulus of w times cosine theta, where theta is the angle at which both vectors diverge. Have a look at figure 3, right? So v and w, they diverge at an angle theta because they're both going in opposite in different directions. I mean, they're both diverging from their meeting point. That's what I mean. Okay, now now how am I going to prove this claim? Now, to simplify calculations, what I'm going to do is I'm going to rotate both v and w in the same way until until w is parallel to the x direction, or the I hat direction. Right, notice this. Notice what happens in figure 3. W is now in the I hat direction, or in the x direction. Now, why can I do this? I can do this because if I rotate 2 vectors in the same way, then their dot product or their inner product remains invariant, and we will see this when we look at rotation matrices later on. Now, since the dot product remains invariant, what I'm going to do to simplify calculations is that I am going to rotate w and v such that w is parallel to the x-axis. So in that event, the y and z components of w are 0 because it is parallel to the x-axis. Now, so what happens is that the dot product of v and w is then v1 times w1, because the other two terms, v2 times 0 plus v and v3 times 0 are both 0. Now, so the dot product is v1 w1. But what is the value of modulus of v times modulus of w times cosine theta? Well, okay, so let's work it out. So from the okay, so modulus of w is just w1 because it has only one component. Now let's keep the modulus of v as it is. Now what is cosine theta? Now cosine theta is OP in the diagram in figure 3 divided by the modulus of v. But what is OP? OP is simply the x component of the vector v, right? Because we've dropped it perpendicular in the x direction. So OP, we haven't dropped it perpendicular in the x direction. OP is basically v cosine theta, right? And v cosine theta leaves only the x component, right? So OP. So what is the x component of v? It's v1, right? So OP is just v1. And so cosine theta is v1 over the modulus of v. So we end up, so modulus w modulus v cosine theta is basically w1 v1. But w1 v1 is the same expression. W1 v1 is exactly equal to v dot w by definition. So we have proven that v dot w equals modulus of v times the modulus of w cosine theta. Now there's only one ingredient in the proof that we are left to do, and that ingredient is this statement that rotating two vectors leaves the dot product between those vectors invariant. And we will look at this once we've looked at matrices. Okay, so what does that tell us? That tells us that the dot product, intuitively, it measures the degree of overlap between two vectors. If they're parallel, right, then the dot product is a maximum, right? Modulus of v times the modulus of w. Now, if the vectors are orthogonal, by orthogonal I mean perpendicular, because you can say perpendicular in 2 or 3 dimensions, but in the more once we switch to n dimensions or an arbitrary number of dimensions, we're going to have to use the term orthogonal, right? So if theta equals pi over 2, as in the angle between the two vectors is 90 degrees, then our vectors are orthogonal, right? Then the dot product is equal to 0 because cosine theta is 0. But as theta goes to 0, as theta gets smaller and smaller, then the dot product gets larger and larger. Now, on the other end, and if they're anti-parallel, meaning if theta equals pi or 180 degrees, then the dot product is a minimum. Then v dot w equals the negative of modulus of v times the modulus of w. Right. So, because cosine theta must be less than or equal to 1 and must be greater than or equal to minus 1, there is a limit on the modulus on v dot w, right? So v dot w must be less than or equal to the modulus of v times the modulus of w, but it also must be greater than or equal to the negative of that quantity. So we have the expression, the modulus of v dot w is less than or equal to modulus of v times the modulus of w. This is in 2 or 3 dimensions. Now this statement also holds for higher dimensions. It holds for an arbitrary number of dimensions. We will prove that in future, but we haven't proven that yet. So now, using so this inequality given the equation 7 is known as the Cauchy-Schwarz inequality, right? And we what we can use this inequality to prove another inequality known as a triangle inequality, which says that the modulus of v plus w is less than or equal to the modulus of v plus the modulus of w. Now, why do we call this a triangle inequality? Notice that v plus w is the third side of a triangle that contains v and w. Remember, this is what we did when we looked at vector addition. So v plus w is x, right? And x is the third side of the triangle. So the modulus of x must be, now if you remember from high school geometry, the third side of a triangle must be less than or the sum of the other two sides. Now, but here it says that the sum of two vector, the modulus of v plus w is less than or equal to the modulus of v plus modulus of w. Now, equality holds when v and w are parallel. But let's go back to this diagram. When v and w are parallel, then x is just v plus. Then we don't have a triangle. That triangle collapses into a line. All right. So in that case, if that is the case, then v plus w, the modulus of v plus w equals the modulus of v plus the modulus of w. Okay. So from 7, we're going to prove 8. You're going to have to prove 8. Now this is part of your first assignment, right? Now if you look at if you want to get started early, it's in the Gilbert Strang textbook, problems 19, 20, and 21. All right then. So that concludes the first lecture. Now, if you have any questions, please put them on Slack, and please ask me during our consultations. I would rather you ask me either on Slack or during the consultation on Tuesday, as in the day right after the lecture. All right. Thank you very much for